Well guys, I'm back. We'll be going over some more of this math and theory. I wanted to finish up on the inductor a little bit. One thing I wanted to talk about was we went over I'll put it down here. Went over how we got about a 90-degree shift between E and I, with E leading, or the voltage leading the current lagging by roughly 90 degrees. Well, there's one other thing that goes on in these coils is helps cause the lag in I is the counter EMF. Well, the counter EMF starts showing up at about 180 degrees and flows up and back down at pretty much the same level within reason of your initial voltage that you're applying. I mean, there is slight differences in it, and can be a little bit differences in the phase, but in an ideal circuit it'll be 180 degrees out, and that's why they call it counter EMF. Now, something else I want to talk about on the coil, and that is the Q of the coil, which is also, when you got like a tank circuit or any filter circuit, it's also the Q of that resonance circuit. And Q is nothing more than X sub L divided by series resistance, and the resistance generally is the wires, which you can neglect. They're going to be short, so there's not going to be much there, but it's primarily the resistance, the DC resistance of the coil, which can be just a few ohms to several hundred ohms depending on frequency of the the coil was designed for. So you take the X sub L in ohms and divide it by the resistance or series resistance of the coil, and that'll give you Q. You want Q to be as high as possible. Q stands for quality. The higher the Q, the less loss you have in the circuit, in the resonant circuit. It don't attenuate as much at resonant frequency. But also, the other thing too is, the higher the Q, the narrower the bandwidth, which is shown here. When you got a really decent high Q, you have a real selective circuit. It's very narrow band. You get a lot of signal through it. When the Q is a little lower, it starts broadening out. And really low Q gives you an extremely broad band. When I start building the radio, we're going to talk about tuned circuits, and naturally, because you got to tune the radio, and this will also come in very important in that, and we'll talk about a little bit of history of radio, the various different circuits that they went through until you get to the super heterodyne receiver. And this will become extremely important too in that discussion. Now let's talk about capacitors. Now, capacitors, when you put an AC signal into a capacitor, now DC signal, you know what happens. It charges up the capacitor, blocks it, that's it, no more flow. AC can get through the capacitor, but of course, according to the X sub C, or the capacitive reactance, 1 over 2 pi FC, it does have some resistance to the AC depending on the size of the capacitor and the frequency. The smaller the capacitor, the higher frequency you can run through it. Now, in capacitors though, the waves are reversed. The current actually leads by 90 degrees versus the voltage. Now that comes from what that comes from is the fact that it takes a certain amount of time for the charge to build up on the plates of the capacitor. You can see this when if you take an ohm meter and decide to put it across capacitors and check them that way, you will see this in there where if you got a real small capacitor, you know, a few hundred picofarads, or even like a 0.01 microfarad or 0.001 microfarad, it quickly builds up to infinite ohms. In other words, it charges up real quick. But if you take like a 20 or 30 or 40 microfarad electrolytic and put on there and start checking it, it's going to take a while for it to build up the charge. Well, that time it takes is what causes this lead of current. The current will still flow as it charges the capacitor and builds up charge on the capacitor before you actually start getting a voltage to actually show up there on that capacitor and in the circuit. So it leads by approximately 90 degrees. In a perfect world with no resistances in anything, these leads and lags will be exactly 90 degrees. It's not a perfect world. But it's all due because it takes a little bit of time to build that charge, to get the charges to move and build up on the plates and shift on the plates. So that's what you get. That's why you get the lead and current over voltage. Now, how do you remember this? The leads and lags of between these two. Well, there's a little saying you can say, a little sentence. Eli the Iceman. Eli, E's before I, so E leads in L circuit, L, Eli, L for inductor. Eli the Iceman. I leads E in ice. C for capacitance. So Eli the Iceman is a great way of remembering it. Now, another thing about capacitors that you'll have to deal with at some point in time or another, and you should really know a lot about, or at least have a good idea about, especially when you're working on anything electronic with capacitors and resistors, is what they call the time constant. Right here, T equals RC. If you're, say, working on a radio and you got a capacitor in there that you know is bad, you're going to replace it, but what if you don't have the right size? How far smudging can you go with that? Can you get by with doubling the size of that capacitor or halving the size of that capacitor? Sizes start becoming very important in these circuits. T equals RC, it's just the resistance times the capacitance. If T's in microseconds, resistance will be in ohms and capacitance in microfarads. So you just multiply the resistance in ohms times capacitance in microfarads, and you'll get the time constant in microseconds. These can get extremely long. You can put really large capacitors and really large resistors in a circuit and spread this out for hours, even depending on the how large you go with the capacitor and resistor. In fact, one thing you'll find that it can vary, any one of these two can vary too, because there's a direct relationship between time and either value. So even if you have a reasonably small capacitor or capacitance, but the resistance is extremely huge, your time can be quite a while for it to discharge, and vice versa. So it's kind of important to pay attention, especially one area, well, any area in the radio is important, but one of the areas is like your AVC circuit, automatic volume control circuit. There's a time constant RC filter in there, generally around 2 megohm resistor with a 0.05 as a general size capacitor. If you start fudging either one of those too much, up or down, it can affect how the AVC works. The whole purpose of that RC filter in there is so that the AVC can still work as far as a weak signal versus a strong signal, or a signal that is slowly fading in and out and trying to keep the volume on the same level, but is not affected very much by just the normal changes in tone and level of the audio signal that you would have when you're listening to whatever you're listening to, whether it's music or whatever. You know how you can go up and down in that volume just a little bit in that audio, so you want to be able to keep that so you can have your fidelity good, but at the same time you want the AVC circuit to do what it's supposed to do. So, and there's some design considerations, but that's where that comes from, is that time constant. So if you start changing out like that capacitor and say it had a 0.05 in there, and you decide, well, the only thing I've got is, you know, a 0.2, and you throw it in there, it's going to drastically change that time constant, which is going to have a drastic effect on how the radio works and how the AVC circuit works. So it is kind of an important formula just to keep in your head, and it's pretty, you know, it's reasonably simple. TRC, T equals RC. Now you have X sub L and X sub C. You have resistances, you have all kinds of different things that's in that circuit. There is one other thing that you hear thrown around quite a little bit, and it's called impedance. Now impedance comes from looking at these here, either one or both, and the resistance of that's in the circuit, the series and parallel resistances. And a standard formula, there are other formulas for this depending on what kind of filter that there is, and I am going to make up a formula chart to put on in my Google Plus Drive thingy on there. Sorry, it escaped my mind what it is. Since now I've learned how to share it, thanks to Art. He was patient enough to walk me through it. But anyway, I will put a bunch more than what I've got here and explain them a little bit so you know what they are. But Z is used for impedance. And the standard formula is the impedance equals the square root of your resistance that's in the circuit squared and your reactances that's in the circuit squared. If you only got one, like say R and X sub L, then this will be X sub L. If you only got C, it'll be X sub C. If you got both, then this equals this. The total reactance is X sub L minus X sub C. And the reason X sub C is subtracted by X sub L comes back to this here and how they react with each other when they're together. So it's standard procedure that X sub C is negative and X sub L is positive. But you subtract these two, that gives you X, you square it, add it to what resistance that's in that circuit, square it, take square, or add them together and take square root, and you get your total impedance. And that works for everything, whether it's the impedance that you're looking at going into a tube, like the input of a tube at the grid circuit, or the plate impedance, cathode impedances, filter impedances, and so on. This can actually be pure resistive. You can actually have no capacitor or anything, or capacitor, resistor, or inductor, and have nothing but just a resistor. and then it just works out the square root of R squared, which is just R, so your impedance just ends up being the resistance. At this point, I think that's about all I've got for you on this. Like I said, I'm working on it right now, and I'll publish out a paper on this. Oh, one other thing I just remembered is the right hand and left hand rules dealing with inductors. Okay. There are two rules that deal with electromagnetism and wires and inductors and stuff when you've got voltage and magnetism. One's the left hand rule, and hopefully my fingers will allow me to do this. I gotta find my piece of wire. There we go. Anyway, alright. My left hand has a little dilemma, but this is your left hand rule. It's the direction of flux. This is the direction of the induced voltage, or EMF, and this is the direction of the conductor movement, either moving the conductor or the magnet. So if I bring a conductor up through this way through the flux, the voltage will go this way. If I rotate it around, then it goes the other direction. You know, whichever way, you can rotate the flux around, whichever way, but that's the left hand rule. So anyway, this, and I'll find me, I'm no artist, so I won't be able to actually draw this out, but I'm sure I think I got a book or two that I can get something out of that may have a picture of this, and I'll put that on there too so that you can remember it or look it up and have it. Now that's when this is more or less the induction of voltage into a conductor, but it also works with how the counter EMF is developed and stuff, because as the AC signal goes through, it's building up a flux, so the flux is moving, so if it's moving in this direction, the voltage can go this way and will be actually in the counter of the direction that you're actually supplying it to. Now one other thing is, like I said before, there was when you do supply a voltage to a wire, a current going through the wire, then there will be a magnetic field created, and that's can be found with the what direction it's going and everything with the right hand rule. And the right hand rule, the thumb shows the direction that your current is, and the fingers wrap around showing the direction of the flux or the magnetic field. Now one other thing, you know, this is all fine and dandy, but if you got a magnet, what is the direction of the flux? What actual direction it is? Or a magnet or a magnetic field of any kind, it's always from north to south. So the north pole of a magnet or a magnetic field to the south pole. That's the direction of flux. So at this point, I think this is enough theory and math for the time being, and in the next video we'll get to doing some construction and building, so I think everybody would be kind of happy to get to that point. But this gives you something to mull on. Like I say, in a couple days I'll have all this and other, well, I think I have some of these on there, but I'll put more on there, and some other stuff for your own information that you know, you can just look at it and study if you want. And we'll talk, you know, I'll come up and try to find some pictures for the left-hand rule, because for me to try to draw that is going not to be very easy. So anyway, until next time, thanks for your comments and stuff, and I'll get back to you on the next video. Thank you.